Okay, so in this video, we're going to analyze vectors, and vectors are often used in physics to represent various components such as force, or maybe in some cases distance. Um, and so we have three methods that we're going to use for this lab. The three methods, the first being the graphical method. The second will be the analytical method, but the third method is the experimental method that you'll use either, if you're online, you'll use a simulation, or if you're face-to-face, you'll use something similar, maybe a force table of some kind to look at the different forces. And so for the graphical method, I'm going to use my laser pointer again. It's also called the tip-to-tail method, or the triangular method, or the polygon method. They're all the same. And it requires that you draw your vectors as accurately as possible using a straight edge and a protractor. Now, I was short of tools here, so I just simply used a box, actually my stylus box. Had a little makeshift box, and I used something from my toolbox, so I just used my triangle that I used to cut wood with. And so let's go through an example here so you can kind of see what we're doing. And this is very similar to what you see in the book. So we're going to be given two forces, F1, which is 0.2 G newtons, and F2, which is also 0.2 G newtons. That should be newtons right there. F1 is at an angle of 30 degrees, and F2 is at 120 degrees. Now G, we need to be cognizant of, G is not grams, and that does not correspond to gram. It corresponds to the acceleration due to gravity. So in this book, this author tends to use things in multiples of G. So I like to just convert it out and write it all out. So it's about 1.96, or about 2 newtons. Makes things a little bit easier for me. And so for F1, I'm basically going to draw a vector that corresponds, and here's where we need to be as accurate as possible. And I need my scale to be as accurate as possible using the graphical method. So I drew out a vector that was about 6 inches long. So for me, 6 inches corresponded to about 2 newtons. So this is maybe a tad less than 6 inches. All right, and then I had to rotate off the horizontal axis, or the x-axis, 30 degrees. And then the same thing for F2. I took F2, I put the tail of it on the tip of F1, and I connected F1 and F2. Remember, I had to rotate F2 120 degrees from the horizontal. And the resultant is this red vector here, which has some magnitude and some direction. We'll figure out the magnitude in just a second, and we'll look at the direction at the tail end of this. And so we can figure out just by measuring. I measured the vector R, the resultant vector. I just, again, took out my straight edge, and I measured it as accurately as I could. And I measured it to be about 7.5 inches. And so since my scale was for every 6 inches, there's about 2 newtons, I calculated this to be about 2.5 newtons. And we'll see later on how accurate I am. All right. And so the second method that you're going to look at is you're going to look at the analytical method. And so the analytical method requires that you be able to decompose, sorry for the movement here, requires that you be able to decompose vectors, and we'll do a decomposition in order to add and subtract the comparable components. And we're going to look at I-hat vectors, or I-hat components, and J-hat unit vectors. And typically this is more accurate than the graphical method. The graphical method gives us a visual of what we're trying to see here. And so we're going to look at the same two vectors, F1 and F2. Remember, G corresponds to the acceleration due to gravity. And we're going to try and find the resultant, we call it R. Now, if you notice here, you see that I've drawn a little arrow above the vectors. That means I'm looking at vector notation as opposed to magnitudes. When I don't have a vector notation above, I'm looking purely at the magnitude in this piece, but this is the I hat unit vector that makes this whole thing a vector. So we have a vector, a unit vector plus a unit vector multiplied by some number. And so when we decompose F1, we'll get 1.7 in the I hat direction or the X direction. So this distance here up to right here is about 1.7 units. And then in the J direction or the Y direction, this distance here corresponds to about 0.98 in the J direction. And we do the same thing for F2. One more time. So it's the magnitude times the cosine of the angle, magnitude times the sine of the angle for the Y direction. And now we've decomposed F1 and F2 into their I hat and J hat unit components. So let me zoom in a little bit here, because essentially all I'm doing to find R is I'm simply adding the X components or the I hat components. So 1.7 minus 0.98 and we get 0.72, and same thing for the J hat components. So 0.98 plus 1.7 gives me about 2.6 J hat. So if I go back up to this vector here so you can get a visual, you should see that in the I hat direction, so this distance right in here should be roughly about 0.72 units in the X direction, right? This distance here, I'm kind of focused on that red vector. And in this direction here in the J hat or the Y direction, this distance here should be roughly about 2.68 in the Y direction or the J hat direction. Okay. And so finally what we want to do is we want to figure out the magnitude of R. So the magnitude of R is equal to, remember, if I don't have a vector above it, or if I put it in absolute value signs, and some books may just write it out without either one of these, so just pay attention to your book. I'm talking about the magnitude here, so when I do the magnitude, basically I'm just using Pythagorean theorem, and I calculate this to be about 2.8 newtons. A little bit off from what I had up above here. Remember when we did that graphical method, and I used a box, my stylus box, but not too bad. And then the direction of R, we'll call it phi. I didn't draw it in this, in this graph here, but phi corresponds to this angle off the x-axis to R. And so finally, the direction of R, we find that by using tangent inverse, and we get about 75 degrees. So hopefully this will help you get going. Remember, the third component is the experimental values. To figure out the experimental values, you use either your simulation or you use an experiment such as the experimental component, such as the force table in class. All right, good luck.